This is our lesson 4.2, capacitors in series and parallel connections. Capacitances and voltages vary from one capacitor to another. Some values have been standardized and may not fit accordingly in an array of applications. This may be solved by using what is called an equivalent capacitor, which is a capacitor that contains the same amounts of capacitance as the combination of capacitors in a given system. Through this, it is possible to find easier approaches to determine the values of unknown variables in the circuit. Two of the most common and simplest combinations that permit the use of equivalent capacitors are what are referred to as series and parallel connections. Capacitors in series. Figure 4.2.2 shows a series connection with two uncharged capacitors connected by wires from point A to B. These capacitors will then begin to be charged as soon as a constant voltage between 2 points A and B has been applied. Recall that capacitors consist of two parallel conductors in figure 4.2.2. The top conductor of C1 gets a positive charge, Q, which results in the negative charge being dragged down the bottom conductor of C1. These negatively charges came from the top conductor of C2 as it has been charged positively. The net charge on the bottom conductor of C1 and the upper conductor of C2 is equivalent to 0. The entire picture also explains how the magnitude of a charge on all plates remain constant. Equivalent capacitance of a series combinations. For capacitors in series, such as the one presented in figure 4.2.2, the voltage add up as follows. VAB equals VAC plus VCB. The following variables VAB, VAC, and VCB may simply be denoted as V1, V2, and V, respectively. And their mathematical equation is given by V divided by Q equals 1 divided by C1 plus 1 divided by C2.
So figure 4.2.3 shows an equivalent single capacitor may be used to substitute the two capacitors in the series connection in figure 4.2.2. So this equivalent capacitance denoted as C. EQ of the series connection refers to a single capacitance in which the charge is similar throughout the combination. So and the voltage is the same. So, for the capacitors in series, the magnitude of the charge must be similar throughout all the plates of the capacitor in the series connection. So, the voltages of the capacitors are not of the same value unless their corresponding capacitance are. So, this equivalent capacitance is series is given by an equation 1 over CEQ equals 1 over C1 plus 1 over C2 plus, so where EQ is the equivalent capacitance of series combination and C1 and C2 are the individual capacitances. So, capacitor in parallel. So, in figure 4.24 shows two capacitors in parallel connected by wires. So, between point A and B, as the diagram indicates, the voltage of VAV in a parallel connections is similar in each capacitors. Thus, VAV equals B is contrary to that in series connection. However, the charge of Q1 and Q2 are not equal magnitudes, and the net charge of the combination is given by Q over B equals C1 plus C2. So, figure 4.2.5, equivalent single capacitor of a parallel combination as illustrated in figure 4.2.5. The net charge is the summation of all the individual charges. So Q equals Q1 plus Q2. So the equivalent capacitance of a parallel combination, the equivalent capacitance of parallel combination is expressed as follows. So CEQ equals C1 plus C2. So where CE is the equivalent capacitance of charge of parallel combination, and C1 and C2 are the individual capacitance. So for the capacitor in parallel, the voltages are similar throughout all capacitors. The charges on the capacitors are not of the same value unless they have similar individual capacitances.
So now on to example number 1. So now here we have the problem. Assign the following values to the variables of the schematic diagram below. Here we have a series connection with both charge 1 and charge 2. Now, the first step to any problem or solving any problem is to identify what was asked. We were asked to solve the equivalent capacitance in the systems. Next is we need to identify the given of the problem. So now we were given the first capacitor and the second capacitor, which was 5.5 mu F and 1.3 mu F. Next is to write the working equation, which would be 1 divided by CEQ, or equivalent capacitance, equals to 1 divided by charge 1 plus 1 divided by charge 2. Next is to substitute the given values. So it would become 1 divided by 5.5 mu F plus 1 divided by 1.3 mu F. The next step, the last step, would be to answer. So it will now add up to 1.05 x 10 to the power of negative 6, which, if we remember, is the value for the milligrams or micrograms, I mean. And that's the answer. The equivalent capacitance in the series connection is 1.05 mu F, or microgram F. Let's go on to the example number 2, the average level. So in this example, we need to determine the equivalent capacitance of the system as well as the charge on each capacitors. Now we need to identify what the problem is. Again, we were now asked to calculate both now the equivalent capacitance as well as the charge on each conductor, conductor 1 and conductor 2. So now we were given capacitor 1 and capacitor 2, which is, for the capacitor 1 we have 12.13 microgram F and 10.20 microgram F, and with the VAB, or the voltage AB, which is valued at 20 V. Now we should remember that the capacitor or the connection is in series. That is a very important fact. Now the next step would be to write the working equations. We have both working equations, one for the equivalent capacitance and the other for the charge on each capacitors. So for the equivalent capacitance, it would be 1 divided by C1 plus 1 divided by C2. And for the charge, which is Q, by the way, is equals to the value of the equivalent capacitance times the voltage. So the step after that would be to now substitute the given values. So now it would be 1 divided by 12.13 x 10 to the power of 6 plus 1 divided by 10.20 x to the power of negative 6, which would be valued or equal to 5.6 x 10 to the power of negative 6 F. So now the charge, as we remember, it is CEQ times V. So now we have the equivalent capacitance. We just have to multiply it with the voltage, which is 20. Now we find the answers. So the answer for the magnitude of the charge, or the Q, is 1.1 x 10 to the power of negative 4C. And for the equivalent capacitance, which we all know, is 5.6 to the x 10 to the power of negative 6F. Now, for example number 3, a difficult level. Here we have our question, which would be to assign again the following values to the variables of the schematic diagram below, and then solve the equivalent capacitance of the system, the charge on each capacitor, and the potential difference for each capacitor. Now again, the first step would be to acquire what is required in the problem. We were asked to calculate the equivalent capacitance of the system, the charge on each capacitor, and the potential difference for each capacitor. Next step would be to again identify the given problem, which would be the first capacitor, which is 8.0 mu f and 4.0 mu f, and the potential difference of 22 voltage or V. And note that our capacitors are parallel or are in parallel. Now for the third step, we are now be able to write the working equations. So we have 2 or 3 equations for the equivalent capacitance for a parallel combination, which would be C1 plus C2. So we're not going to divide them by 1 like the in series. Next, for the charge on each capacitor, it's also very different. So since for Q1 it is C1 multiplied by V, and for Q2 it's C2 multiplied by V. And for the potential difference, it's already just given. There's actually no equation for it. It's just VAB is equal to V, which is 22. Now substitute the given values. For the equivalent capacitance, it is 8.0 x 10 to the power negative 6 plus 4.0 x 10 to the power negative 6 F. And for each charge, for the Q1, it is 8 times 10 to the power negative 6 F times 22V. And for the Q2, or the charge 2, is 4.0 x 10 to the power negative 6 F times 22V. Now we just find the answers. For the equivalent capacitance, if we add it all together, we have 12 mu F. And on each capacitor, for Q1, we have 1.x 10 to the power of 4, negative 4 C. And for charge Q or Q2, we have 8.8 x 10 to the power of negative 5 C. And for the potential difference would be just 22V. Now for example number 4, difficult level. So assign the following values to the variables of the schematic diagram below. Now solve the equivalent capacitance of the parallel and series combination. So it's both actually. So it's a series as well as a parallel combination. The C2 in C3 is parallel, and both the C2 and C3 are a series combination of the C1. First step, of course, we were asked to calculate the equivalent capacitance of the parallel and series combination. Next, we identify the given, which is the first capacitor, which is the 1.0 mu F. Second capacitor, which is 2.0 mu F. And the capacitance of the third capacitor, 3.0 mu F. So again, the capacitors are a combination of in series and in parallel. First thing we have to do is for the working equations. So the first one, for the parallel combinations, we need to find the equivalent capacitance of it. In order to do that, we have to identify what was the parallel combination, which is the C2 and the C3. So you have to add those together. Next, for the equivalent capacitance of the in series, which is the equation for this is 1 divided by CEQ is equal to 1 divided by the C parallel, or the equivalent capacitance of the parallel combination, plus 1 divided by C1. Next is to substitute all the given values for the CEQ, or for the parallel combination. 2.0 mu F plus 3.0 mu F is equals to 5.0 mu F. And for the equivalent capacitance in series is 1 divided by 5.0 mu f plus 1 divided by 1 point mu f. So now you just find the answers. Thus, our equivalent capacitance of the series and parallel combination is equal to 5.0 mu f. So, lastly, we now find the answers. So, the equivalent capacitance of the series and parallel combination is equal to 5.00 mu f. And that was all. I am Jean Kyle Flores, and together with my partner sister Giselle Macula, that is all. Thank you.